Welcome to the week 7 of our calculus course. This week we will be doing a lot of graphing of different functions, including ones that have asymptotes. So today we're going to review the definitions of the asymptotes relying on the concept of the limit. Have you ever heard a saying that the asymptote is a line that function tries to touch but never ever allowed to? Well, this is oversimplification. While there are some functions that never touch their asymptote, there are infinitely many functions that not only touch their asymptotes, vertical, horizontal, or slant, but even cross one. Let's clear up any misconceptions and define exactly what makes a vertical, horizontal, or slant asymptote. A line x equals a is a vertical asymptote of a function f of x if the outputs of the function f of x explode to plus infinity or minus infinity as the input x gets closer and closer to value a. This means that the function can be exploding to plus infinity or minus infinity on either side of x equals a. Here are examples. We can see that the vertical line x equals 0 is an asymptote of the first function because as x goes to 0 from the left side and from the right side, function value drops to minus infinity. Example number 2 has two vertical asymptotes. One is at x equals minus 2 because as x approaches minus 2 from the left, function explodes to plus infinity. Observe also that as x approaches minus 2 from the right, function value explodes to negative infinity. Something similar but opposite happens around x equals a. In the third example, as the input x approaches value minus 1 from the right, the output values of the function go to minus infinity. This behavior of a function is what makes an asymptote x equals minus 1 a vertical asymptote. Notice how, as x approaches minus 1 from the left, values of the function try to get closer and closer to 2, and indeed becoming equal to 2. So this is an example where a function f of x touches its vertical asymptote. We just dismissed the myth that an asymptote cannot be touched. A line y equal L is a horizontal asymptote of the function f of x if, as x goes to plus infinity or minus infinity, output values of the function f of x try to get as close as possible to value L. A function can have as many as two horizontal asymptotes. In our first example, the limit of the function f of x as x approaches plus infinity is equal to pi over 2. This what makes a line y equals pi over 2 a horizontal asymptote of a function. Limit of the function f of x as x approaches minus infinity is equal to minus pi over 2. This behavior makes line y equals minus pi over 2 a second horizontal asymptote of a function f of x. In the second example, we see line y equals 0 a horizontal asymptote of the function f of x, because the limit of the function f of x as x goes to plus infinity is equal to 0. On the second example, you can see how function f of x crosses its own asymptote infinitely many times. The third example shows that the limit of the function f of x as x goes to plus infinity is equal to 1. This what makes horizontal line y equals 1 a horizontal asymptote of the function f of x. Observe also that function f of x crosses its horizontal asymptote in example number 3. A line y equals mx plus b is a slant or oblique asymptote of the function f of x if the gap between the function f of x and the line mx plus b goes to 0 as x approaches plus infinity or minus infinity. By considering the gaps shown in examples 1, 2, and 3, we can see that, indeed, the function tries to behave like a slant line mx plus b in each particular case. So let's work on an example trying to understand how can we use limits in order to identify horizontal, vertical, and slant asymptotes. Let's show that the function f of x has all three types of asymptotes: vertical, slant, and horizontal asymptotes. Function f of x is a piecewise function, where if x is strictly less than 2, it's given as 10 divided by x minus 2. And if x is greater than 2, it is equal to 2x squared plus 3x minus 4 divided by x minus 2. Here is a graph of a function, and we can see that function indeed has lines that it tries to behave like as x approaches the point of discontinuity x equals 2, or as x goes to plus infinity, minus infinity. The good candidate for the vertical asymptote is the point of discontinuity. So let's take a look if a function has a vertical asymptote at the point of discontinuity x equals 2 where function is not defined. By calculating limit of the function f of x as x approaches 2 from the left, we see that the values of the function go to minus infinity. This means that a function indeed has a vertical asymptote. On the other side, as x approaches 2 from above, we also notice asymptotic behavior. The values of the function explode to plus infinity. So the function around x equals 2 truly tries to behave as a vertical line x equals 2. Now let's study behavior of the function as x goes to negative infinity and positive infinity. A function f of x has a horizontal asymptote y equals 0 because when we look at the outputs of the function f of x as x approaches minus infinity, we see that the function tries to become equal to 0. Limit of f of x as x goes to minus infinity is equal to 0. However, we can also observe that the limit of the function f of x as x goes to plus infinity is not equal to 0. Indeed, the outputs of the function go to plus infinity. So the horizontal line y equals 0 is a good illustrator of asymptotic behavior only when x goes to minus infinity, but not when x goes to plus infinity. Let's prove that function f of x has a slant asymptote 2x plus 7 by calculating the gap between the function f of x and the slant line y equals 2x plus 7. We can do this very easily by calculating limit of the difference 2x squared plus 3x minus 4 over x minus 2 minus 2x plus 7. When we find common denominator and simplify numerator, we'll get in numerator 18 and in denominator x minus 2. As x goes to plus infinity, this quotient goes to 0. Therefore, y equals 2x plus 7 indeed is a slant asymptote of the function f of x. But how do we find an equation y equals 2x plus 7 of the slant asymptote for the function f of x? As x goes to infinity, function f of x defined by the quotient 2x squared plus 3x minus 4 divided by x minus 2. This is a rational function where in numerator we have a polynomial of degree 2 and in denominator we have polynomial of degree 1. Since the numerator has degree exactly 1 higher than the denominator, we can use long division to rewrite 2x squared plus 3x minus 4 divided by x minus 2 as an whole part plus the remainder divided by divisor x minus 2. As a very first step, we need to figure out what we can multiply x by so that the result of multiplication is equal to 2x squared. Multiplying 2x by x creates 2x squared. But we'll also need to multiply 2x by negative 2, which gives us minus 4x. By subtracting from the first line 2x squared minus 4x, we will get 0x squared. 3x minus minus 4x is equal to 7x. Also from the first line, we'll copy minus 4. We know that multiplying x by 7 will create exactly what we need, 7x. But we will also need to multiply 7 by negative 2. Subtracting from 7x minus 4, 7x minus 14, we will get 0x minus 4 plus 14 is equal to 10. Since 10 has the smaller degree than x minus 2, the divisor, we need to stop, as we have found the remainder of the long division. So the whole part is 2x plus 7. The remainder is 10, and the divisor is x minus 2. We can see that as x goes to infinity, our function f of x tries to behave as a line 2x plus 7, because the gap between the 2x plus 7 is equal to the remainder divided by the divisor, 10 over x minus 2. That gap goes to 0 as x goes to infinity. And this is how we find equation of a slant asymptote, y equals 2x plus 7. In all cases where we have a function f of x as a rational function where numerator has degree 1 higher than the denominator, completing a long division allows us to extract equation of a slant or oblique asymptote. So here we are discussing asymptotic behavior of a function f of x. We're studying what's going on with the outputs of the function when x approaches plus infinity, minus infinity, or the point of the discontinuity. By looking at the values of the limit, we're able to determine what kind of asymptote function has, if it has any. This week in class, we'll do much more graphing, and some of the functions we will graph will have asymptotes, so I hope you have found this review useful. Until next time.